Every photographer obsesses over lenses, over megapixels, over glass. But there is one component sitting quietly at the heart of every camera, from the one in your pocket to the ones launched into orbit, that decides more about your image than almost anything else. It's not the lens. It's not the software. It's a piece of light-sensitive silicon barely larger than your thumbnail. It's the sensor. And its size changes everything. Before we talk about size, let's talk about what a sensor actually does. A digital camera sensor is a semiconductor chip, typically made of silicon, covered in millions of microscopic light receptors called photosites. Each one of those photosites corresponds to a single pixel in your final image. When you press the shutter, light floods in through the lens and strikes the sensor surface. Each photosite absorbs photons, the fundamental particles of light, and converts that energy into an electrical charge. The brighter the light hitting a given photosite, the stronger the charge. That charge is then measured, digitized, and recorded. Do this across millions of photosites simultaneously, and you have a photograph. It's essentially the digital evolution of film, but instead of silver halide crystals reacting to light, you have silicon. Fast, precise, and extraordinarily sensitive. So where does size come in? Here's where it gets fascinating. Not all sensors are created equal. In fact, the range of sensor sizes used in consumer cameras today is staggering. At the smallest end, we have the 1/2.3-inch sensor, found in basic point-and-shoot cameras and budget smartphones. It's roughly the size of a grain of rice. Step up, and you find the 1-inch sensor, used in premium compact cameras. Then there's Micro Four Thirds, used by Olympus and Panasonic mirrorless systems, about 4 times the surface area of a 1-inch sensor. Above that sits APS-C, sometimes called a crop sensor, used in most entry-level and mid-range cameras from Canon, Nikon, Sony, and Fujifilm. And then there's full frame, 36 by 24 mm, the format of professional bodies like the Sony A7 series or the Nikon Z6. Beyond even that are medium format sensors, found in Hasselblad and Fujifilm GFX cameras, measuring over 50 mm diagonally. These are the giants, used for commercial photography and work where absolute image quality is non-negotiable. Here is the fundamental physics behind why sensor size matters. Think of each photosite as a bucket. When it rains, when light falls on the sensor, each bucket collects water. A big bucket collects far more water than a small bucket in the same amount of rain. A larger sensor has more physical surface area, and if you hold the megapixel count the same across 2 sensors of different sizes, each individual photosite on the larger sensor is physically bigger. It has more area to collect incoming photons. More photons captured per site means a stronger, more accurate electrical signal. And a stronger signal means less noise, less of that grainy, speckled texture you see in low-light photos from small sensors. This is why smartphone cameras, despite having 50 megapixels, still struggle in dark restaurants or evening street scenes compared to a full-frame camera with only 24 megapixels. The megapixel count is a red herring. The photosites on the smartphone sensor are nanoscopic. They starve for light. This relationship also directly governs dynamic range, the camera's ability to capture both deep shadows and bright highlights in the same frame simultaneously. Larger sensors capture a wider tonal latitude. They hold more information before the highlights burn out and the shadows turn to mush. There's another consequence of sensor size that cinematographers and portrait photographers have built entire visual languages around, and that is depth of field. Depth of field refers to how much of a scene is in sharp focus from front to back. A shallow depth of field isolates your subject and the background melts into a silky blur. That blur is called bokeh, and it's the signature look of cinema, editorial photography, and professional portraiture. To capture the same field of view on a larger sensor, you need a longer focal length lens. That longer focal length, by the physics of optics, produces shallower depth of field at any given aperture. A smartphone sensor is so small that even its equivalent focal length is incredibly short, often just a few millimeters physically. Short focal lengths produce deep depth of field. Everything is in focus. It's optically difficult to separate your subject from the background. This is why computational photography, meaning software-generated bokeh on smartphones, exists. It's software trying to replicate what physics does effortlessly on larger sensors. Now let's address something that confuses almost every beginner, and that is crop factor. When you mount a lens designed for a full-frame camera onto an APS-C body, the smaller sensor only uses the central portion of the image circle that lens projects. The result is that the image appears magnified, zoomed in, crop. APS-C sensors have a crop factor of approximately 1.5 to 1.6 times, depending on manufacturer. This means a 50mm lens behaves like a 75 to 80mm equivalent on an APS-C body. Micro Four Thirds takes this further with a crop factor of 2x, so a 25mm lens gives you the field of view of a 50mm. This isn't a flaw, it's a feature that system designers deliberately exploit. Telephoto shooters love Micro Four Thirds because a 300mm lens suddenly reaches like a 600mm. But it also means you cannot simply compare lens focal lengths across systems without accounting for the sensor they're attached to. So why doesn't everyone just shoot medium format? Because size is never free. Larger sensors mean larger, heavier camera bodies. They require larger lens elements to cover the bigger image circle, which means bigger, heavier, more expensive glass. Manufacturing a defect-free sensor at large scale is extremely difficult, which drives up cost dramatically. A medium-format sensor chip costs more to produce than many cars. There are also optical physics limits. Very large sensors become vulnerable to a phenomenon called diffraction, where stopping down a lens too far actually softens the image because light waves begin to interfere with each other. And then there is simply portability. A smartphone fits in your shirt pocket. It's the camera you actually have with you. And the best camera in the world is always the one in your hands. Sensor size is not the final word on image quality. It's a set of physical trade-offs. More surface area means more light, more dynamic range, shallower depth of field, and cleaner shadows. But it also means more weight, more cost, and less convenience. Understanding these trade-offs doesn't tell you which camera to buy. It tells you which camera to choose for the moment in front of you. And that, the intersection of physics and intention, is what separates a snapshot from a photograph.